problem, we think about what happens in a Geiger counter. A Geiger counter has a cylindrical metal tube, so that's this part right here. It has a diameter of 25 millimeters, so about an inch. And inside that is a little metal wire with a 1 millimeter diameter. The wire and the cylinder are separated by a gas, and we know what the dielectric strength is. And the question we're going to try and find is, what is the capacitance per unit length? So first off, let's make sure we know what we're asked for. Pretty often we want capacitance C. This time we want capacitance per unit length. So what is C over L? So regular capacitance C is equal to charge over potential. C over L is going to be charge over potential divided by L. Or Q over L divided by the potential. Q over L, that's the charge density lambda. Okay, now we have a goal. We want to find out what is the capacitance per unit length. So we want to find the charge density divided by the potential. How do we find the potential? Let's think about electric field. So from Gauss's law, we know that the electric field somewhere on the interior of this cylinder is equal to 1 over 2 pi epsilon naught times the charge density divided by the distance from the center r. So there's the expression for the electric field. The electric field is a vector. Let's assume that our outer cylinder carries a positive charge and our inner cylinder carries a negative charge. So our electric field points inward. Now we know we can use electric field to find the potential, so let's write down our expression for potential. Delta V, so V final minus V initial, equals minus the integral of E dotted with ds. In this case, it's going to be minus the integral of minus, so our electric field points inward, our radial component points outwards, minus ER times dr. So that's plus the integral of ER, 1 over 2 pi epsilon naught times lambda over r dr. One more step in the integral here. We'll take our constants out front. Lambda over 2 pi epsilon naught times the integral 1 over r dr. The limits of the integral will start at this inner wire and we'll finish at the outer wire. We want to find the potential difference between the two wires. So we go from RA to RB. Okay, let's just deal with that integral part next and then we'll put it all together. The integral of 1 over r is the natural log of r, evaluated at our limits. So natural log of RB, take away the natural log of RA. We can use the identity of logs that says natural log of A minus natural log of B is the natural log of A divided by B. Now the radius of B, the diameter is 25 millimeters, so the radius is going to be 25 millimeters over 2. Radius of A, the diameter is 1 millimeter, so the radius is going to be 1 millimeter over 2. So the millimeters cancel, the 2's cancel, and we're left with the natural log of 25. So we can plug this in for our integral portion right here. Okay, so now we know our potential. We can plug this in for our capacitance, and we can find the capacitance per unit length. We see that the charge density actually cancels, the linear charge density. We're left with 2 pi times epsilon naught over the natural log of 25. Epsilon naught is 8.85 times 10 to the minus 12 farads per meter. Put that in and we work it out, we get 17.0 times 10 to the minus 12 farads per meter. So there's our capacitance per unit length of this Geiger counter.